Hi, in this short video we want to revisit chapter 2 where we were facing the wind door problem, which was trying to decide how many doors and how many windows should be produced in the available plant hours. So if you recall, we had gotten it to the point where we had developed a descriptive model for the wind door problem. And again, the only decisions to be made were how many doors and how many windows to be produced. And the constraints on the problem were related to the number of hours available for producing these new products at plants 1, 2, or 3. So, if you recall really quickly, one of the complicating aspects of the problem was that the separate products had different profit amounts attached to each. So for a door, each unit would generate $300 in profit, and for windows, it would generate $500 in profit per unit. Now again, the next three rows reflected the constraints of the problem, because naturally, if you make a positive profit for each unit you produce, then the quick answer would be, well, why don't we just produce 1 billion of them and we'll all retire and live in the Bahamas. But clearly what prevents you from doing that is that there are constraints in a problem like this. And so in this case, it was limited in terms of the number of hours at each plant. So plant 1 had 4 hours available, and it required 1 hour for each door that you chose to make. Plant 2 required 2 hours for each window that you made, and there was a total of 12 hours available at plant 2. And then plant 3 actually required 3 hours for each door that you made, or 2 hours for each window that you made, and there were a total of 18 available hours for plant 3. So with this information, we now have we can estimate the total profit depending on how many doors and how many windows we decide to make, and also we know how we do with respect to using our available hours at the respective plants. So this is how we left things in terms of a descriptive model. So now if we move over into the world of prescriptive modeling, we're now asking the question, what's the best number of doors and windows to make each week? So with that, for a two-variable problem like we have here, we can use what's called a graphical method to analyze it. And so let's just walk through that solution really quick. So for starters, we can represent the model algebraically. You remember algebra problems back in high school where you have a variable, in this case it's the number of doors or the number of windows, represented in this case by the letter D or the letter W, and you can write a mathematical expression. So in this case we're trying to maximize profit, which is P, and P is equal to this now linear function of $300 times D plus $500 times W. So that's what we call the objective function in this algebraic representation. Then you're subject to constraints, which in this case are the hourly maximums at each of the 3 plants. So plant 1, plant 2, and plant 3. And then of course you can't produce a negative number of doors or windows, which would be kind of equivalent to selling them back to the company in a way. So we constrain, with these last 2 expressions, we constrain ourselves to only consider solutions where we're producing a positive amount of doors or a positive amount of windows. So, in a two-variable problem like this, we can set an x-axis, in this case to be the number of doors that we're going to decide to produce each week, and the y-axis is the number of windows we're going to produce each week. Now, each of these black dots represents a possible solution to this problem. In other words, down here at the origin, it says don't produce any doors and don't produce any windows. Whereas the black dot here in the middle says, well, let's produce 2 doors and 3 windows each week. And then up in the upper right is a solution which says, hey, let's make 4 doors and 6 windows each week. So again, so you imagine now any point on this graph represents a possible solution, some of them feasible, some of them not, to the wind door problem. So if we restrict ourselves to just positive quantities for the number of doors and the number of windows that that we create, then we're automatically in this quadrant. We can't produce a negative number of doors, we can't produce a negative number of windows, and we can't produce a negative number of doors and windows. So we're only in the world of positive amounts, or at least greater than or equal to amounts. So then what we can do is start now trimming down this feasible region according to the constraints in the model. So plant 1 had the constraint basically that said the number of doors must be less than 4 because it takes 1 hour of plant 1 time to make 1 door, and therefore it basically crops off anything to the right of this vertical line right here. In other words, we can't consider any solutions that involve more than 5 doors being produced. Similarly, plant 2 has a constraint that says 2 hours times the number of windows must be less than or equal to 12. Well, that's effectively saying the number of windows you choose to produce must be less than 6. So that starts to now crop this upper portion of the feasible region. So we've now looked at 2 of the 3 constraints. What about the third constraint? Well, the third constraint, if you recall, was for plant 3, and it said, well, plant 3 is actually used for both doors and windows, and it takes 3 hours for each door on plant 3, and it takes 2 hours for each window on plant 3. So what happens is we can draw a line that represents the boundary that we could possibly produce. So for example, if we produced no windows and we asked ourselves the question, well, what's the most number of doors that we could produce? Then the answer would be 6, and we're down here at this point 6, 0. And again, the way we got that was saying, imagine the windows is 0. What's the most number of doors that we could produce? So 3 times 6 would be less than 18. We do the other thing on the other axis. We basically say, well, suppose we hold the number of doors to 0. What's the most number of windows that could be produced? Well, since it takes 2 hours for each window and we have 18 hours available, that gives a solution of 9 possible windows could be produced at plant 3, assuming we're producing no doors. Now, between those 2 points, the 6, 0 and the 0, 9, you've got basically this line which represents a boundary. And if you check any of the points along this boundary, you'll see that the solutions fully use the 18 hours available at plant 3. So this now represents our third constraint on the model. And basically it says the following: anything like within this triangle would be feasible with respect to plant 3. Anything beyond that line would be infeasible for plant 3. In other words, it would run out of hours on plant 3. So notice, by the way, our constraint had a limit of 18 hours, and that's what gave us this line, 6, 0 up to 0, 9. But notice if the number of hours that were available at plant 3 were different, like if it was 6 hours more, say at 24 hours, it would tend to push that sort of borderline outward away from the origin. Whereas if we have fewer than 18 hours, say we were down to only 12 hours available at plant 3, it tends to move it closer towards the origin. In other words, it tends to more heavily constrain the feasible region. Now, if we now look at it back in terms of how we're now cropping down this feasible region, this is plant 3, and if we bring all 3 of the plant constraints together, it gives us this now form of the feasible region. So again, this feasible region, it's the set of points that obey all 3 of the plant constraints, and it obeys the fact that you can only produce in non-negative production quantities. So this represents, again, what we call our feasible region with this little 2-variable graphical method. I apologize for this annoying window that pops up, but anyway. So now we've got this feasible region. Well, how do we figure out which of the possible solutions in here is the best one that optimizes our desire to maximize our total profit? Well, what we can do is create what's called an isometric profit line in this case. So if we say, well, if we produce 300 windows and 0 doors, we'll have a total profit of $1,500. Correspondingly, if we produce down here 500 doors and 0 windows, we will get a profit of $1,500. And so, in fact, any point along this segment will deliver a total profit of $1,500. So that's what we mean. It's like an iso profit line. So again, any solution along here will deliver us $1,500 of profit. Well, what we can do is imagine we've got this like line now drawn with a ruler, and what we do is we now start sliding that up in the direction of increasing profit. So like if we slide it up here to where it's hitting 10 doors and 0 windows, heck, that's worth $3,000 of profit, which is better than our original $1,500. And again, the ISO profit point over here is 0 doors and 6 windows, which again delivers us, 0 doors and 6 windows, which gives us a total profit again of $3,000. So all of the solutions along here deliver $3,000 of profit. And if we continued to push this straight line with a ruler, we would make our way to the final feasible point, which it turns out is at 2.6, which means producing 2 doors and 6 windows each week. Well, you can cost that out, and that gives you a total profit of $3,600. This represents our best feasible solution for this problem. So again, imagine we've slid this ruler, keeping the slope the same, but we slide it until the very last point where we still have a feasible solution connected to it. So in summary, again, what you do is you identify your constraints and you draw the boundary lines for each of those constraints, and you figure out which side of that line is feasible. And when you get those all together, then that represents the feasible region. Now again, once you have that feasible region established, you determine the slope of one objective line, and imagine now you're starting to slide with a ruler this objective line in the direction of improvement. And you get it to the point where you're now touching the last feasible region in the direction of improvement. And it turns out that will be your optimal solution. Now it turns out in a linear program like this, and we'll talk more about what we mean by a linear program, in a linear program, indeed, the optimal solution will always occur at one of the edge points, and in particular one of the corner edge points typically of the feasible region. More on that later, but I want to give you a quick heads up in terms of the graphical method for solving 2-variable optimization problems like this. Thanks, and we'll see you in class.